Today we're going to take a look at conditional probability and independence. First, let's take a look at conditional probability. The probability we assign to an event can change if we know that some other event has occurred. That's the whole idea of conditional probability. If you are given an extra piece of information, how does that change your probability? The probability that one event happens, given that another event is known to have happened, is called conditional probability. So the conditional probability that event B happens, given that event A has happened, is written using this notation. And you read this, the probability of B given A, or the probability of B under the condition that A happened. So, let's take a look at an example. In 1912, the luxury liner Titanic, on its first voyage across the Atlantic, struck an iceberg and sank. Some passengers got off the ship in lifeboats, but many died. Suppose we randomly select one of the adult passengers from the Titanic, and let's define the events F for first class passenger, S for someone that survived, and T for someone who's a third class passenger. We want to find the probability of T given S, or the probability that someone was a third class passenger given that they survived. So, we know that this person survived, which means that we can narrow down the part of this chart that we are looking at to just the row of survivors. Now, only looking at that row, what is the probability that someone was a third class passenger? That would be 151 out of 442. Which when you divide it is 0.342. I like to think of it as the given information, so given that they survived, that's like the denominator of your fraction. So if you look here, the total number of survivors was our denominator. So I think of this, the T given S, as a fraction. If we're going to interpret this value as in context, the probability that a randomly selected passenger was in third class, given that they survived, is 0.342. Or you can word it in a different but similar manner. For example, given that the randomly chosen person survived, there's about a 34.2% chance that he or she was a third class passenger. Now, let's look at part B. Given that the chosen person is not a first class passenger, what is the probability that she or he survived? We want to write this in appropriate notation. So we know that the person was not a first class passenger. So that means we are looking at F complement. They are not in first class. So we are given that they are not a first class passenger. We want to find the probability that they are a survivor. So we are looking for the probability of S given F complement. So if we go ahead and try to calculate that probability, we are narrowing it down to only look at non-first class passengers. So in this case, second and third class passengers. And we want to know the probability that one of these people survived. So, survivors who were in second and third class, that's 94 plus 151, over the total number of people who were in second and third class, 261 over 627. Go ahead and do that math, and you get 0.276. To formalize this, the official formula for conditional probability, the probability of A given B, is the probability of A and B over the probability of B. Another way of writing that is the probability of A intersect B over the probability of B. Or generically, the probability that both events occur together over the probability that the given event occurs. Now, since it doesn't really matter which event you label A or B, you can switch up the A and the B. So the probability of B given A is the probability of B and A over the probability of A. Let's look at another example. A survey of all residents in a large apartment complex reveals that 68% use Facebook, 28% use Instagram, and 25% use both. Suppose we select a resident at random. Given that the person uses Facebook, what is the probability that she or he uses Instagram? So, we know that the person uses Facebook. We want to find the probability that the person also uses Instagram. So we're trying to find the probability of Instagram given Facebook, or the probability of I given F, where I is that someone uses Instagram, F is that someone uses Facebook. So, using the formula from the previous slide, that is the same as the probability that someone uses both Instagram and Facebook over the probability that the person uses Facebook. Now, those probabilities are given to us. The probability that they use both Instagram and Facebook is 0.25 over the probability that they use Facebook, which is 0.68. Go ahead and divide that, and you get 0.368. Now, we can use conditional probability to determine if two events are independent. If A and B are independent events, that means that knowing whether one event has occurred does not change the probability that the other event occurs. Or in other words, A and B are independent if the probability of A given B is the same as the probability of A given B complement, which is the same as the probability of A. Or if you switch up A and B, the same thing holds. So, let's look back at our table relating gender and pierced ears. If we want to know whether gender and having pierced ears are independent, we need to label some events. So let's look at being male and having pierced ears. The probability of someone having a pierced ear, given that they are male, you've got the probability of B given A, where B is that they have pierced ears and A is that they're male. You look the probability of them being both male and having pierced ears, which there are 19 people who do that, over the total number of people who are male, 90. Divide that, you get 0.211. So, if we look at the probability of B given A complement, so the probability that someone has pierced ears given that they are not male, or in this case female, The total number of females with pierced ears is 84 over the total number of females is 88, which is 0.955. Since these two probabilities are not equal, these events are not independent. Knowing that a student is male significantly changes, or in this case reduces, the probability that the student has pierced ears. Let's look at another example. Is there a relationship between gender and handedness? By handedness, we mean whether you're right-handed or left-handed. To find out, we used a Census at Schools random data selector to choose a simple random sample of 100 Australian high school students, and they completed a survey. We've got the data summarized here in the table, looking at the relationship between gender and dominant hand. Suppose we choose one student at random. We want to know, are the events male and left-handed independent? So, we can start by looking at the probability that a student is left-handed given that they are male, and the probability that a student is left-handed given that they are female. So, there are 7 males who are left-handed out of 46 total males, which gives us a probability of 0.152 of selecting a student who is left-handed given that they are male. Probability of selecting a left-handed student given that they are female. There are 3 female left-handed students out of a total of 54 female students, which gives us a probability of 0.056. Since these probabilities are not the same, they are not independent events. Males are more likely to be left-handed. So if you know that a student is male, then you know that they are more likely to be left-handed than if you knew that they were female. Last topic for today is the general multiplication rule. If we know that 55% of high school students participate in school sports, and that of those athletes, 6% go on to play a college sport in the NCAA. We want to know what percent of high school students, total, not high school athletes, play a sport in high school and go on to play on an NCAA team. Well, based on these sentences, we know that 6% of 55% go on to play a college sport in the NCAA. So if you multiply those out, that's about 3.3%. So, formalizing this a little bit, we're trying to find the probability that a student plays a high school sport and ends up playing on an NCAA team. So, to do that, we need to take the probability that a student plays a high school sport and multiply that by the probability that they are on an NCAA team given that they played a high school sport, which those are the numbers from the previous slide. 0.55 times 0.06, which is 0.033, so about 3.3%. To write this all out with the general multiplication rule, the events A and B both occur. To figure out that probability, you can use the general multiplication rule that the probability of A and B, or remember another way of writing that is the probability of A intersect B, is equal to the probability of A times the probability of B given A. You probably learned back in elementary school that you could just multiply the probability of A times the probability of B. That is only true for independent events. So this is the general rule that applies for events that are independent or not independent. Let's look at one last example. The Pew Internet and American Life project reported that 79% of teenagers, they define teenagers as 13 to 17-year-olds, use social media, and that 39% of teens who use social media feel pressure to post content that will be popular and get lots of comments or likes. We want to find the probability that a randomly selected teen uses social media and feels pressure to post content that will be popular and get lots of comments and likes. So if we're trying to find the probability that a teen uses social media and feels pressure, we're going to start by taking the probability that they use social media, multiplying that by the probability that they feel pressure to post, given that they use social media. And those are the two pieces of information that are given in this paragraph. The probability that a student uses social media is 0.79, and for the teens who use social media, so given that they use social media, the probability of students who feel pressure to post is 0.39. Multiply those together, you get 0.308. Now, if you were given a little bit of different information, you could do the same calculation by just switching events A and B. So here we have the probability of A and B, the probability of A times the probability of B given A. It depends on what information you're given in the paragraph. You could easily switch it so you have the probability of B and A, you have the probability of B times the probability of A given B, and you'll end up with the same final answer. It just depends on what information is given in the paragraph. That's it for today. Go ahead and work on your practice problems.